What's up, chat? What's up, chat? Today we are going to do a couple hours of some Leetcode. Um, just hit a quick workout, so I have the tank top on. But yeah, we're gonna focus on finishing those binary search questions from yesterday. Let's see. Okay, so today we have a lot of stuff planned. We have to review the questions that we haven't reviewed in 5 days. So a bunch of questions. You have over 10 questions. And we also have to finish these 3 binary search questions. So yeah, let's get to it. Binary search. On arrays. Okay. Yeah. So cocoa eating bananas. We were pretty much unable to finish this question yesterday. So we might just look at the question. We might just watch the video solution for this.
Hey guys, Greg here, and let's solve.
Let's watch the Leetcode video.
Cocoa eating bananas, Leetcode number 875. It's a very interesting problem that bananas per hour. This one and then one pile. So in 1 hour, she's only ever going to pick one pile. Now here's the thing.
Okay, I want to ask Leetcode what the optimal solution is first. So I know which video to watch, because I want just the optimal solution. Alright, let's ask Lee, what's the optimal solution for this question? I just made a mango, strawberry, banana, pineapple smoothie. Added my creatine in it. Added some Greek yogurt. This is amazing. Is this optimal? I thought you said use math.seal. Yeah, it's not optimal. Okay, yeah, let's look at this one. What? Okay, well, it's okay. Um, that looks to be that solution. And what was Leetcode's? Leetcode, cocoa eating bananas.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve cocoa. The rate was too small, so we need to
Okay, yeah, let's just use Leetcodes. The code looks a lot more cleaner.
find an even bigger rate. This is a pretty interesting problem because there is a brute force solution that we can arrive at, and that brute force solution arrive at, and that brute force
Okay, stream is good.
solution can easily be transitioned into a binary search solution, which is the optimal solution for this problem. So we're going to be working our way from the brute force to that binary search solution. So Coco loves eating bananas, and we have n piles of bananas given to us in a piles input array. We're also given a second parameter, h, which is the number of hours that we have in order to eat all of the bananas. So we have to eat them within h hours. And so Coco has a certain eating speed where she can eat a certain number of bananas per hour, and that variable happens to be k, and k is not an input variable. That's what we're trying to determine as the solution for this problem. Each hour, she can only choose one pile of bananas and eat k bananas from that pile. So that's what we're trying to determine, that k value. If the pile has less than k bananas, she'll eat all of the bananas, but she's not going to eat any extra bananas from a different pile. So what we're saying here is Coco can only eat at most one entire pile of bananas in a given hour. So what does that tell us? Already we're given some key information. Let's say we're given a certain number of piles, right? So basically the length of P, H must be greater than or equal to the length of P. Why is that? Because let's say we have 5 piles, right? So let's say we had 5 piles, and let's say this is what the piles look like. The values aren't too important, right? 1, 1, 2, 2, 3.
So
And let's say we had
the length of the number. So the number of piles must be less than or equal to. Okay.
H equals 4 hours. Well, let's say K equals some really big number, like 3, right? Basically the max of this input array. Okay, Coco. This entire pile, Coco. Right, this entire pile, and this entire pile, because she could only
Okay, so every hour she can only eat k number of bananas. So, okay.
eat 4 piles because we only have 4 hours, right? Coco can only eat 1 pile per hour. So if she ate all 4 piles over here, we'd still have 1 left over. That's why they guarantee us that H is always going to be greater than or equal to the number of piles. So the minimum in this problem, given this input array, H, the minimum it could possibly be is going to be 5. And I sort of wrote over it, but the last important thing that they tell us in the problem is we want to determine that eating speed K that Coco is going to eat at, but we want to know the minimum integer K, the minimum eating speed of Coco that she could eat all of the piles in exactly 5 hours. Or
So in the first example, she eats, so it's 8 hours, so you don't want to go over 8, so let's start with 3. 3, that's 1 hour, and then 2 hours to eat 6, so total of 3 hours, and then another 2 for 7, so that's 5, and oh, sorry, actually. So for 3, it would be 1 hour for the first pile, 2 hours for the third, 3 hours for 7, and 4 hours. So that would be 4 plus 3, 7 plus 3. So that would be over 8. Let's try 4. 1 hour, 2 hour, 2 hour, 5 plus 3 hour, 8. Okay.
or exactly whatever that time interval, that number of hours happens to be. So let's take a look at this example. They give us an input array of 4 piles and they give us 8 hours to eat all 4 of those piles. What's the minimum K, the minimum eating speed that Coco could use to eat all of these piles in at most 8 hours? So we have to eat all the piles in 8 hours or less. Well, the brute force would be to start at 1, right? Because Coco could try K equals 1, right? Can we eat all piles in 8 hours then? Well, it will take us 3 hours to eat the first pile, right? 3 divided by 1, which is our K, right? 3 divided by 1 is going to be 3 hours to eat this first pile. And to eat the second pile is going to be even more. That's going to be 6 hours, right? 6 divided by 1, 6 hours. So far we already have 9 hours, and we haven't even eaten the entire number of piles. So therefore, K equals 1 is not going to work. And we could just continue this brute force approach, right? Now try K equals 2, right? And then do the exact same
So how can we use a binary search to find K? That's a
computation with
interesting
K
way.
equals 2. Now, my question to you is, we know that the minimum possible solution would be K equals 1, right? K can't be 0 because that would mean we're not eating any piles. So the minimum is 1. What's the maximum that K could possibly be given this input array and given this number of hours? Well, remember, the number of hours is always going to be greater than or equal to the number of piles. So in the worst case, K would basically be the max number that happens to be in our piles. For example, if K equals 11, right, that means we're able to eat the max pile in exactly 1 hour, right? And if we can eat the max pile in 1 hour, that means every other pile is also going to take us only 1 hour. So therefore, we're going to eat every single pile in 4 hours. And we know for sure that this is going to be less than whatever is given to us as H, right? We guaranteed that at the beginning. So really what we're doing here is we're going to try every single value from 1 all the way up to 11, which happens to be the max value of our piles. And the first value that we get that allows us to eat every single pile in less than or equal to 8 hours is going to be our output. So we're going to end up trying 1, we're going to end up trying 2, we're going to end up trying 3, and we're going to find that 4 allows us to eat all the piles in less than or equal to 8 hours. So this is not a terrible solution, right? Even though we're brute forcing the entire solution set, 1 through the max of piles, it's not going to be terrible. What's going to be the complexity of that? Well, we're potentially going to have to iterate through every value in this potential solution set, what's that going to be? Well, 1 through the max value of our piles, right? So it's going to be, let's say, big O of the max value of piles, so max of P, multiplied by the length of P, because for every K value, we're potentially going to have to try, okay, if I eat all these, how many hours is that going to take me, right? So we're going to have to iterate through this entire array for every K value that we try. So we're going to get a time complexity of max of P multiplied by P. Right, but that's only, we're getting this max P from the fact that we're having to iterate through every single value in this K range. But why should we iterate from 1 to the end of that K range? Why, in which case, in the worst case, we'll have to go through every single value. Why don't we instead apply binary search on this K range? What's that going to give us? Well, we can reduce max of P to the log of max P. So if we can improve this, this is what our time complexity is going to be. Okay, so I ran out of room, but this is the improved time complexity. Basically, we're taking this variable and applying a log to it, which is going to reduce it a little bit. So let me show you quickly how that binary solution is going to work. It's pretty straightforward, and then we're going to jump into the code. So we're going to be using binary search. We're given this input array, and we want to eat every single pile in less than or equal to 8 hours. So we know that the potential rate that we're eating bananas at, K, is going to be between 1, that's the minimum it could possibly be. The max it could possibly be is going to be whatever the max in our input array is. We know the max value is 11. We can find that in linear time. So then we're going to initialize a range like this, right? This entire range that we have, going all the way from 1 to that max value 11. So in other words, we're going to have a left pointer at the minimum and a right pointer at the maximum. Then we're going to compute the middle by taking the average of left and right. 1 plus 11 divided by 2 is going to be 6. So our middle is going to be here. In other words, our K that we're trying is going to be here. This is the rate that we're going to eat bananas at. So we're trying the rate of 6. Does this work? Can we eat all these bananas with a rate of 6 bananas per hour in less than or equal to 8 hours? Can we do that? Well, how many hours does the first pile take? Well, 3 bananas, right, divided by the rate, which is 6, is going to round up to 1. That means it took us 1 hour to eat the first pile. The second pile, 6 divided by 6, is also going to take 1 hour. So let's just count the number of hours. So the third pile, 7 divided by 6, is going to round up to 2. So that's going to take 2 hours. The third pile, 11 divided by 6, is going to also round up to 2. That means 2 hours. So we just did this in 6 hours, right? Is that good? Does that mean we found our solution? Well, 6 is less than or equal to 8. That means we were able to eat this entire thing in the time threshold with a rate of 6 bananas per hour. Is this our solution? Well, remember, we were looking for the minimum K value that allowed us to do this. So this might be the solution, but let's try all the smaller values, or let's start our binary search in this direction to see, is there a smaller value than 6 that we can use for our K value? So basically what I'm doing here is, if we're able to eat the entire pile in the threshold, what I'm going to do is then start searching in the left direction. So what I'm going to do is take my right pointer and shift it to K minus 1, because now we're searching this entire range. What if the opposite was true? What if I tried this K value, but I was only able to eat the entire banana pile in, let's say, H equals 10 hours? That means I went over the threshold, right? That means I went over the time. So what does that mean? Does that modify our binary search? Well, what that tells us is our rate of eating bananas, 6, was too small. We didn't have enough time to eat all the bananas in the given available time. So what we have to do is increase our rate of K, right? So in that case, what I would do is I would search the right portion of the range. So what I would do is take the left pointer and set it to K plus 1 over here at the 7. So that's how this binary search is going to be working. But so far we do have one possible solution, and that's 6. So now our new right pointer is pointing over here, and our result is for now going to be 6. So once again, we're going to take the left and right, add them together, divide by 2. That's going to give us 1 plus 5 divided by 2 is 3. So our K is now going to be at this 3 value. So now let's check. Can we eat all the bananas in less than or equal to 8 hours? How many hours does the first take us? Well, we're eating at a rate of 3 bananas per hour. The first pile is 3. That's going to take us 1 hour to eat it. The second pile, 6 bananas divided by 3. That's going to take 2 hours. The third pile, 7 divided by 3, rounding up, is going to be 3 hours to eat that pile. Last pile, 11 divided by 3, rounded up, is going to be 4 hours. So when we total all of this up, it's going to give us, I think, 10 hours. So just like we discussed before, we went over our threshold. We took too long to eat these bananas. So what that tells us is this did not work. 3 bananas per hour doesn't work. Let's start searching to the right of our range. And remember, when we took this right pointer and shifted it, what we basically did was we said that none of these values are ever going to be considered again. We're now searching in the other range. That's how binary search works, remember? So since this did not work, we're not searching it, and we're not going to search any of the values to the left of it. So what we're going to do is take this left pointer, set it to k plus 1. So once again, we're going to take our pointers, add them together, divide by 2, and in this case, we'll just round down. So 9 divided by 2 is going to be 4. So I'm going to put my k value basically where left happens to be at 4. So let's see, with a rate of k equals 4, can we eat all the bananas in less than or equal to 8 hours? The first pile takes 1 hour, the second pile takes 2 hours, the third pile takes 2 hours, and the last pile takes 3 hours. So totaling all of this up, we get 8, right? So we were able to eat all the bananas in less than or equal to 8 hours if we had a rate of 4. So basically, let's compare that to our current result. So far, we found a value with 6. So really, we can update this 6 and say there's a smaller rate that we can use that happens to be 4. So now that we did find a potential result 4, let's see if we can find an even smaller one. Remember, that's what we did before. If we find a k that works, we're going to try to find an even smaller one. So what we're going to do is we're going to set our right pointer shifted over here. But notice how now the left and right pointers are not in the correct order, right? Left should always be to the left of the right pointer. That's basically how you know that our binary search has stopped. We don't have to continue the binary search anymore, right? And that makes sense because now we're searching values that we previously crossed out. We crossed these out, so how can we search them again? It makes no sense. So now we can stop the binary search and we can return the current result, which happens to be 4. 4 is the minimum rate of bananas that Coco could eat to eat all bananas in less than or equal to 8 hours. With that being said, let's jump into the code now. So just like I mentioned, we are going to have our left and right pointers initially set to 1. Left is going to be 1 and right is going to be the max that happens to exist in our piles input array. Now the result, we're not going to initialize it to 0 initially because remember we're looking for the minimum. So I'm just going to initialize it to R, which is the max in our piles because we know at least this will work. This is the max that our solution could possibly be. And now we just start binary searching while our left and right pointers are in the correct order. We can compute the k by adding the left and right together and dividing by 2. And we want to count for this value k, for this rate k, how many hours does it take to eat all bananas? So let's initialize hours to 0 and go through every pile in the input array piles. So for any given pile P, we can divide it by K, which tells us how many hours it took. But remember, we have to round up. So there's a function in Python, math.ceiling, which will round this up for us. And whatever that happens to be is what we can add to our hours total. Once we've done that, then at the end of that loop, we're going to check if hours happens to be less than or equal to H, the given input. If it is, that means we can update our result to a new minimum, right? Take the minimum of the result and whatever K happens to be. K is that
math.ceil P. Okay, so that's the value divided by the midpoint K. If hours is less than or equal to H, res equals min res K. Okay, yeah. So we're trying to find the minimum. As long as it's less than hours. Cool.
rate that we're looking for. And if this is the case, then how are we going to update our binary search? Well, we're going to look for an even smaller k. So what we're going to do is set our right pointer equal to k minus 1. We're going to search the left portion now. If this wasn't true, how would we update our binary?
Our right pointer is going to be k. So if it's if hours, it's less than the excuse me. So if the hours if it takes less time than it's needed, we can move our right pointer to the midpoint and subtract 1, because that means that if the hours is less than h, that pretty much means that um, so if it takes less hours than necessary, that means we can increase the number, or sorry, decrease the rate at which she's eating, because basically she's eating at a higher rate, or we can search for a lower rate because she is eating fast enough for there to be less time allocated, or else if she's taking too long, we are going to have to increase it.
Search in the opposite case. Then we would take our
And
left pointer and set it to k plus 1, because that means the rate was too small, so we need to find an even bigger rate that will allow us to eat the bananas in the given time interval. And at the end of this loop, once the binary search has stopped, we know that we're going to be returning that result variable, which tells us what the minimum k happens to be. And believe it or not, that is the entire result. So I hope this was helpful. If it was, please like and subscribe. It supports.
That was very helpful. Okay. So for this question, now that we understand it, let's just go over the solution line by line and comment it. So first we're going to initialize our left and right values, and then we're going to set our, instead of 0, because we know it can't be 0, we're just going to set it to the max, and then find the minimum of the value while we loop. So this is the basic binary search. While the left pointer is less than or equal to right, our midpoint, k is going to be calculated, and then we're going to find the total number of hours at rate k. So for this, we loop through the values in piles, and then we add the p divided by k value and use math.co function. And now, if the hours is less than k, we can first add it. We can set as a solution and find the min to find our answer, and then move the right midpoint, or else we move the left midpoint up, because eating too slow. We just return res. Okay, let's submit it, and then let's add it to our tracker. Alright, so initialize left and right pointers to track k. So that's 1 to max, or max, what was the function? Max piles. Then binary search. Basic binary search. While left is less than or equal to right. Midpoint k is going to be right plus left divided by 2, or 2. And then, so we calculate the midpoint, and now we want to use that value in piles. So for p in piles, if p initialize hours for p in piles. P at hours is going to be plus or equals math CL piles P divided by K. And then if the hours is less than or equal to, was it H? We can shift our right pointer if our else shift our left pointer and then return ends. Okay. Okay, cool. That's it for Coco. Let's take a quick break, chat, and we're gonna look at the next question. Find minimum in rotated sort array. Okay. Find minimum in rotated sort array. Okay, chat. We'll be right back. I'm gonna use the restroom and take my contacts out and do a couple other things. But yeah, I'll be back in maybe around 10:25, 10:30. See you guys soon. contacts. What's up, chat? Just got changed. Took out my contacts. Feeling good. Feeling good. Ready to do the next question. I feel good. Let me check my stream to see if my stream is up real quick. Feeling good. Feeling good. Ready to do the next question. I feel good. Let me check my stream to see if my stream is up real quick. Feeling good. Feeling good. Ready to do the next question. I feel good. Okay, let's get this. Let's do it. All right. So this next question: find minimum in rotated sorted array. All right. Let's do this question and. I don't know if we'll be able to do the other two. Let's try. Let's aim for both of these two questions, and then I'll have to end stream because I have class. But yeah, so I'll try to do two questions. If not, one is fine, and then we'll finish up this last question. And then I'll start reviewing these day 5 review questions. I think that's a good plan. Yeah. Okay. All right. Let's get it. Let's start it. So. Okay, I see what's happening. So the array list, each rotation means 0 goes to n, 1 goes to shifts left. Okay, so I understand the brute force on the rotations. Notice that rotating an array A0, A1, A2, and minus 1 time results in the array. Okay, got it. So basically it's just saying one rotation. So this line is just saying that one rotation leads to the new value just being unique elements return the minimum element of this array. Sorted rotated array. What? Minimum. Bro, can't you just do like nums min or min nums? I don't know how this is a binary search question. Yeah, right? This question is so, I don't get it. Yeah, this is a uh, really easy question. It's just a normal sort. Oh, it's not. Huh. If nums are right is... Oh, that's smart. Okay. So it's basically saying that if the last element is greater than the first element, there's really been no rotation. Because if we rotated it to 1, 2 would be greater than 1. So, or if you wrote 1 there and then 2 there, 1 would be less than 2. So we know there's no rotations. And so if it is, rotated. What's up, Uyong G6R? If it is rotated, then if it is rotated, then nums at right is greater than nums at 0. If it is rotated, while right is greater than or equal to left. So that means if right is okay. So it's just like some math stuff. Okay, I get it. Let's watch the video and then let's just try to code it without looking at the code. But yeah, this makes sense to me. So let's go ahead and check that. So we have 2 more of those we have to finish. This is probably really similar. So yeah, so let's go over find minimum and rotated sort array, go over search, and then we'll try to fit in time-based key value store, or I might do that off stream, but try to do that by before it gets too late, and then we have to review all those questions. So yeah, let's do it. Search and rotated search. Fine.
That was originally... Okay, let's solve...
Okay.
Leetcode 33 search and rotated sorted array. So we're basically given an array that was originally sorted like this one, but then it became rotated like this one. And by rotated, they mean that they took a certain pivot or index of the array, like right over here, and then they cut it in half and then swapped the portions, right? So you can basically think of this right-hand portion being swapped over to the left side over here, right? That's what happened, as you can see here. Right, these 2 halves were put in the opposite position. And we're also given a target value, in this example, target 0, and we want to check if our array contains this value. If it does, we return the index. If it doesn't, we return -1. The most straightforward way to approach this problem is literally just check every single value.
Whoops, my bad. This is the right question.
Hey everyone. Hey everyone, welcome back. This our target. Let's write some more neat code today. So today let's solve the problem find minimum in a rotated sorted array. So we are given an input array of length n. Be 6 and given this number of hours. Well, remember, already we're given
Left pointer.
n that is assorted in ascending order, but it could be minimum in a rotated sorted array. So we are given an input array of length n that is assorted in ascending order, but it could be rotated 1 to n times. For example, if we have an array like 1, 2, 1, 0, 1, 2, right? To rotate it by 1 basically means to take the rightmost element, move it to the beginning like this, right? So this has been rotated by 1. We could also rotate it by 2 by taking the last 2 elements and moving them to the beginning. So something like this, right? This has been rotated by 2. And so we want to find the minimum value, and we want
Is
by
that right?
2, the beginning. Assorted in ascending order, but it could be rotated 1 to n times. For example, if we have an array by 1 basically means
Wouldn't it be 2, 0, 1? And 2 rotations? Oh, I don't think that's right. 4, 5, 6. We just add to the back, so it'd be 2, 0, 1.
to take the rightmost element, move it to the beginning.
What?
Like, hey everyone, welcome. If we have an array like 1, 2, 1, 0, 1, 2, right? To rotate it by 1 basically means to take the rightmost element, move it to the beginning like this, right? So this has been rotated by 1. We could also rotate it by 2 by taking the last 2 elements and
Okay. Okay. 201 after run rotation, and then 120.
moving them to the beginning. So something like
Yeah. Okay.
this,
120.
right? This has been rotated by 2. And so we want to find the minimum value, and we want to do it in log n time, as they say. The
Log
good
n
thing
time.
is that we do have some kind of sorting property that we can use to our advantage to find this log n time solution, and we are guaranteed that every value in the array happens to be unique. Of course, it would be easy to find a linear time solution, basically just scan through every single value in the array and then take the minimum value and return it. But we can use the sorting property to our advantage even if the array has been rotated. Let me show you how we can do that solution. As you might be able to guess, it is going to involve the binary search algorithm, which is usually the algorithm that runs in log n time. So the fact that the array was originally sorted is what hints to you that binary search might work in this case, but it's not going to be a traditional binary search. Now, of course, if the entire array was rotated n times, that basically means we took a sorted array such as 1, 2, 3, 4, 5, rotated it n times, basically leaving it in the original sorted order. Now, if we had an array that was completely sorted like this one, an easy binary search would work on a sorted array, but if the array is fully sorted, then we know that the minimum value is going to be the leftmost, right? So if at any point we get binary search is going to run like this, a left pointer and a right pointer. If we ever get to a point where the entire array is sorted, we can just return the leftmost element, or at least consider this as being the minimum value.
Right.
So let's try a binary search and see how it's going to be different than a regular binary search. Now, of course, we want to find the minimum value. We're going to initialize our left pointer here and our right pointer here. Basically, the current pointer situation means that we are considering this entire array to find the minimum. The minimum could be from anywhere in this array. And the result is going to be the minimum, and I'm going to keep track of that over here. Now, of course, one way we could do this problem is basically find the pivot, right? Find the position where, the elements are not in increasing order, right? From here to here, 3 to 4, they're in increasing order. From 4 to 5, they are in increasing order. From 1 to 2, they're also in increasing order. But from 5 to 1, they're in decreasing order. This is the pivot, right? So basically, this value is going to be the minimum. But I'm going to do it in a slightly different way where we don't necessarily have to, look exactly for the pivot. I'm going to take, left, right, take the half of them, get our middle pointer. Our middle is going to be over here at 5. So I'm going to consider as 5 being the minimum value we have seen so far, right? So our result is going to be 5. Now we have to ask ourselves, okay, this could have been the result, but now we don't want to, look at this value again. So the question becomes, are we going to search to the left or are we going to search to the right? Where are we going to find the minimum value? Where are we going to find a value that's even smaller than 5? Well, first consider this. Since we rotated the array, we have 2 portions of the array that are sorted, right? We have this portion of the array that's sorted, the left portion, right? And we have the right sorted portion of the array, which is also sorted. So the question is for us, with this middle pointer, at this value 5, are we currently in the left sorted portion, or are we currently in the right sorted portion?
So if 5 is...
Now, if we are in the left sorted portion of the array, don't we want to search the right sorted portion? Reason being, if we rotated the array, the left portion is always going to have values that are greater than every value in the right sorted portion, right? Because when we rotate, right, suppose an array like this, we're taking the rightmost value, the largest value, and putting it over here, right? So we're taking larger values, putting them on the left side, right? So therefore the values on the right are going to be smaller now. So that's why it's always going to be that way. So if our middle pointer is currently in a value that's in the left sorted portion, then we want to search the right sorted portion because it has smaller values in it, right? So how can we know if we are in the left sorted portion? Well, like I said, every value in the right sorted portion is going to be smaller than every value in the left sorted portion. So one thing we can check is if the current middle value is
less than
greater
or Okay, yeah. If it's less than or equal to, or if it's greater than
Greater than or
or equal
equal
to.
to the value all the way at the left
If the current value is greater than the all the way to the left.
of our thing, right? Because the left value is going to be the smallest value. If
Because the left.
the middle value is greater than or equal to the leftmost value, that means this middle value is a part of this left sorted portion, right?
Okay.
In which case we want to search to the right. Now, if our middle pointer, suppose in this case we can see 5 is greater than or equal to 3. The reason we're doing greater than or equal is technically this middle pointer could actually be at the left position as well. That's one edge case. And in that case, we would also, this would be the left sorted portion. But suppose our middle pointer, instead of being at 5, was actually over here. It was at 1. What would our condition evaluate to then? Nums of middle would be 1. Is that greater than or equal to the left value, which is 3? It's not, right? Because the values in this right sorted portion are going to be smaller than the left sorted portion, in which case this would evaluate to false, right? If it's false, that means, if we're at a value that's in the right sorted portion, then we want to search to the left, right? Because in this case, the right, if our middle was at this, it makes sense that, okay, all the values to the right of it are going to be greater. So then we want to search to the left.
This is a popular question. Google, Microsoft, Amazon.
But obviously these values are also greater, but that kind of doesn't illustrate the point, because what if our middle pointer was over here, right? Maybe we had some values over here. This is where our middle pointer is. We see 2. Okay. 2 could have been the minimum. Then we want to search to the left because we want to find even smaller values. Particularly, we would want to for some random reason. Let's just see how our binary search would work in that case. Well, we would take this middle value, say that it might be our result. I mentioned we are going to be maintaining a result. Now, we can set this to some arbitrary default value. I'm just going to set it to nums of 0. We could just pick any value in the input array nums, but I'm just going to choose the leftmost just because. We're also going to have our 2 pointers. Initially, left is going to be...
All right, chat, we're going to take a second. We're going to take a second. I'll be right back.